Hi, everybody. Good evening. Are you guys there? I see 1, 2, 3, 4, 5, 6 of you. Hariharan, are you there? Srikriti?
Yes, sir.
Okay. Srinidhi? Abhinav?
Yes, sir.
Okay. Srikriti 2 times. Why? I think have you joined with 2 devices, Kanna? Srikriti? Okay.
Sir, and one device my audio is not clear, sir, and one device I'm using it for video.
Understood. Okay. Murali?
Yes, sir.
Okay. Right. So my name is Akash. Right. This is going to be a first session. I think we'll be seeing us quite a few number of times after this, I guess. Right, till your portion is completed. Okay. So okay, may I know what chapter is going on with you?
Chemical bonding.
Chemical bonding is going on. Okay. Chemical bonding hybridization is done.
Sir, we were only seeing the geometry of those compounds with lone pair and without lone pair.
With lone pair and without lone pair, geometries you were seeing. Okay, fine. Maybe we'll start from there. Okay, fine. Sir, we need to start VSCPR theory. Okay, fine, Srinidhi. We'll take it. Right. Okay. So certain things before we start the class, right? So first thing is if you have anything, right, you can just unmute yourself, you can just ask whatever you want to ask, right? And second thing is you'll understand once I start writing that my handwriting is not going to be that great, right? I will write light legibly as much as possible, but if you don't understand anything, right, you will again stop me right there and ask, sir, what is that? What are you writing? You can ask. Okay, right? And the class will be interesting. You don't have to worry about, the classes with the boring class, not able to listen and stuff like that, right? So, and I would really advise you to take as much as notes as possible. Like whatever comes out of my mouth, whatever I write, everything is going to be important. Everything is going to be golden for you, right? Okay, so actually, as much as you're going to record, as much as you can extract whatever is going to come out of the lecture, as much as benefit you're going to get, right? Okay, very, very simple points. All you have to do is listen, and all you have to do is write properly and then ask the questions whenever wanted, right? Okay, with that being said, let me share my screen. Right. Okay. Right. So you're telling me that we're talking about geometries and shapes. Someone said VSCPR. Okay, right. So I don't know where exactly you are, right? So let me ask you with simple questions, right? I don't know where exactly you are. Okay, so if I take this molecule CO2, right, and if I ask you what is the hybridization of this molecule, what is the answer? Okay. If I ask you in this particular molecule, how many sigma bonds are there? How many pi bonds are there? What is your answer? Come on, it's okay. Even if you're wrong, you can tell me at least whatever you think it is.
2 sigma bonds, 2 pi bonds.
Okay, that's good. Right now, everybody knows how to draw Lewis dot structures. I hope. Is there anybody who don't know what is Lewis dot structure or how to draw the Lewis dot structure? Is there anybody who's like that? It's okay. Nobody is going to judge. If you don't know, you can say you don't know so that I can help you. Is there anybody who doesn't know? Okay. So I'm going to assume the fact that everybody knows what are Lewis dot structures and how do you draw them, right? Okay. So if you draw the Lewis dot structure, this is what you will get, right? Carbon in between, and oxygen's valency is 2, so it is always going to form double bond. And carbon's valency is 4, so it needs to form 4 bonds. These are some common things you have to remember or you should know, right? Okay. So now we always know that the first bond formed, right? The first bond which is formed is always a sigma bond between any 2 atoms, right? Between any 2 atoms, if at all there is only one single bond, that bond is always going to be sigma, right? On top of that, how many ever bonds you form? That is on top of sigma, already a single bond. If you form a double bond or a triple bond, more than triple bond is not possible again, right? So if you have double bond or triple bond, the both of the extra two bonds are going to be pi, right? And again, in this case, the first bond formed between your carbon and oxygen is sigma, and on top of that, how much ever you form is pi, right? So you see one sigma, two sigma, second sigma, and first pi and second pi, 2 pi's, right? Okay. Say if I ask you in N2 molecule, right? How many sigmas and how many pi's? In N2 molecule, how many sigmas and how many pi's?
1 sigma, 2 pi.
Okay. So now there is, if you can draw the Lewis dot structure, okay, we'll draw the Lewis dot structure, okay? We'll see how is it, right? So for Lewis dot structure, all you have to understand is octet is going to be the criteria, right? And for you to have one covalent bond, right? One covalent bond, I need 2 electrons, right? Anyways, I understand. So now nitrogen, if you check, right, it is going to have atomic number of 7. So you will write the configuration to be 2,5, right? Now we have to understand that obviously in a bond, only the valence electrons are going to participate. That is, the electrons that are there in the valence shell, the last shell, those electrons will only participate in the bonding. When I say bonding, we're talking about sharing of electrons, transfer of electrons, whatever it is in case of ionic and covalent bonds. So in those things, only your valence electrons will participate. So that alone only have to take care for, account only for your Lewis dot structures, right? So we have to draw 5 electrons for nitrogen. So 1, 2, 3, 4, 5, right? And there is one more nitrogen also, that is also going to have 5 valence electrons, and I'm going to draw like this. Okay. Now, if you check for octet, right, we know that 8 electrons should be there in the valence shell, right? So now already 5 electrons are there, right? So 3 more electrons are required for each of the nitrogen atoms, right? So what I understand is this nitrogen is going to take the 3 electrons of this nitrogen, and this nitrogen is going to do the same thing, right? So it's not like when I say take, it's like taking it out. It's like this nitrogen takes electron away from this nitrogen. No, it's not like that, right? So it's like if this electron is going to come somewhere closer, this electron of this nitrogen will come set closer, and both these electrons will be shared between these 2 nitrogen atoms, so that 3 electrons goes to this extra, 3 electrons goes to this nitrogen extra, right? Okay. So what I was saying, yeah. So now for as I told you, for each covalent bond, right, we require 2 electrons. Now for each pair of electron getting shared, we will draw 1 bond, and we for each pair of electron 1 bond, another pair of electron 1 bond, right? Now you see that there is going to be a triple bond between your 2 nitrogen atoms, right? And obviously you see that there are 2 more electrons left out that you will represent like this, and these are what are called as your These electrons, what are they called as?
Lone pair.
Lone pairs, right? So how do you define what lone pairs are? Lone pairs are valence electrons. Obviously, they are valence electrons, but which is not going to take part in bonding, right? Even though there are 5 electrons here, right? But out of them, only 3 electrons are involved in bonding. 2 electrons are not involved in bonding. They're still there in the valence shell, right? Those kind of electrons, if it is paired, then it is called lone pair of electrons, right? Okay. So now we understood that between 2 nitrogen atoms, I have a triple bond. So obviously, as I said, the first bond formed is always sigma. On top of that, how many other bonds you form are all pi. So pi and again pi. Total, you will have 2 sigmas, 1 sigma and 2 pi's, right? Okay. So these are all just to test or refresh wherever you were. Okay. So then that is one thing. Okay. Now what is the difference between your sigma and pi bonds? The both are chemical bonds, both are covalent bonds, both are formed by sharing of electrons, right? So what is different?
Sigma bonds are single bonds and pi bonds are double bonds.
So 1 sigma bond and 1 pi bond I take, right? So both are formed by sharing of electrons. Both are, for example, single bond only. What is so different? Why are you naming them different? What is that sigma and pi?
Pi bond is weaker than sigma bond.
Okay, that's true, but that doesn't answer my question. Do you know something about overlap of orbitals? What does VBT says? Your valence bond theory, right? Right? What does your valence bond theory says? It says that if you have to, I don't know, can someone tell me a statement of what exactly it says? Fine, I don't want to waste time. Then we'll directly, you can take down what it says, right? VBT says that a covalent bond is formed. A covalent bond is formed when unpaired valence electrons gets paired. That's it, as simple as that, right? So all you have to understand is a covalent bond is formed when unpaired electrons gets paired, right? When unpaired electrons gets paired, in the sense unpaired electrons of the bonding atoms gets paired. Now, how you'll understand this is, for example, let us say the simple molecule like hydrogen, H2 molecule is there, right? So we know that hydrogen is having a configuration of 1s1, another hydrogen is having a configuration of 1s1, right? That is, I have these two electrons are there. Okay. Yes, we know. Do you know about these s orbitals, p orbitals? How to write the electronic configuration? I hope everybody knows, right? Okay. So each of these hydrogen atoms are having single electrons like this. Okay. Now what is going to happen is, now we know that there is a covalent bond formed between your hydrogen and hydrogen atom. There is a single bond that we know, right? Now what VBT says is that this covalent bond is formed by mutual sharing of electrons. Yes, but how that happens is, this s orbital which is there for hydrogen and this s orbital is having there for hydrogen, and each having electrons like this, right? Now they will come and overlap like this, and the electrons will be shared like this. That is how you imagine how the sharing of electron takes place, right? The orbitals will get overlapped, they will get mixed, and in that process the electron gets paired, and in that process a covalent bond is formed, we say, right? Okay, so that's what is exactly saying, right? So now it's all about how the overlap is happening, right? So whenever a covalent bond is formed, that happens when the orbitals having unpaired electrons comes together, gets clubbed, gets paired, and covalent bond is formed. This is very, very important to understand, right? Fine. Now, what are the types of overlap we can have, right? Now, for example, if I take S overlap, that we already saw, this is exactly whatever you are seeing here is nothing but your SS overlap. Two s orbitals overlapping to form a bond where unpaired electrons are there and they get paired, right? Now, what other kind of overlaps you can have? Say I can have a s orbital and a p orbital overlapping, right? For example, if you want to take an example for this sp overlap, so let us take a molecule like HF, right? Now you see that hydrogen is going to have 1s1, that is the configuration, and fluorine is going to have 1s2, 2s2, 2p5. Right now, the valence shell is only second shell, and that too, if you check for 2p5, this is how you write the configuration, right? Sorry, 2p5. 1, 2, 3, 4, 5. Right? This is how you write the configuration 2p5. Right? Okay. Now you see that this is the unpaired electron we're talking about. Right? So what you understand is that your s orbital is having one electron like this, right? And this p orbital which you're seeing here, right, that is having the unpaired electron which is coming from the fluorine. I told you only the valence shell participates, the inner shell doesn't participate in bonding, right? So now you will have this p orbital. Okay, let me draw it a little more clearly. Okay, coming straight like this. Okay, and this is having an electron like this. Okay, now they both will overlap so that you will get something like this, right? And so that this hydrogen F bond is, this is how this paired electron is existing, this bond pair, this electron is involved in the bond formation, It's the one electron coming from each of hydrogen and fluorine. Right? This is sp overlap. This is an example for sp overlap. Okay. Now, when you go to pp overlap, right? Now, one possibility that now if you can remember the shapes of the orbitals, we know, like if you are wondering what am I doing here with the circles and some dumbbells, you all know, so those should know that s orbitals are spherical in shape, your p orbitals are dumbbells in shape, and your d orbitals are what shape?
Double double.
Double dumbbell shape. Right. All of them are double dumbbell. In d orbitals, are all the d orbitals double dumbbell?
No.
Okay, which is different.
DZ square.
Okay, that's good. Right. So dz squared, we know, I don't know how many of you remember the shape. Dz squared is going to look like this. We are going to have this is your z-axis, and surrounding this, I'm going to have a ring. Right? If this thing is going like this, I'm going to have a ring here surrounding the dumbbell. So that is not exactly double dumbbell. Anyways, okay. So now you see that this is how sp overlap happens. Now when you go to pp overlap, right? When you go to pp overlap, now there can be two possibilities of how a p orbital can overlap. Okay. One possibility is head-on collision. Say for example, like I have an electron here, I have an electron like this, right? And then they will be able to make a bond here, right? This pair, this electron, this is the part where electrons are present. Okay, this is one type of possibility, right? This we can call it as head-on overlap, right? Like heads are colliding, right? Okay. Now another possibility is that, say the p orbitals can come like this, right? Right. This is some other kind of overlap. Say the p orbitals comes like this. I hope you're still looking at the video. The p orbitals coming like this. That is one possibility. P orbitals coming like this. Another possibility. Right. So this is the first way you're seeing head-on overlap. This. Okay. Now what can happen here? You will see that. Wait. So this part becomes your bonding, right? Okay. So this is your PP. Now this what can I call this? This kind of overlaps or what are called as your lateral overlaps, right? And this kind of overlaps are what are called as head-on overlaps. Okay. Right. Now, if you look at s orbitals, for example, s orbital was able to do only one kind of overlap. Which kind of overlap is that? Again, I'll repeat my question. S orbitals was able to do till now in SS overlap and SP overlap. S orbital was able to do only one kind of overlap. Which type of overlap is it? There are two types, right? Head-on overlap and lateral overlap, right? So what is happening in case of s orbitals? Which overlap is happening? I don't know what is the confusion here. It's very simple, right? It's head-on overlap, right? S orbitals are already spherical, right? How will you talk about head and tail first of all? That doesn't make sense, right? S orbital is spherically symmetric. It's like a ball. It can only do head-on collision, right? So all you can understand is in SS overlap, in SP overlap, I can have what? I can have only head-on overlaps. I hope I am making sense. Right? Only head-on overlap is possible when s orbital is involved. But only when p orbitals are involved, there is two possibilities. Head-on overlap is possible as well as lateral overlap is possible. Right? Now, whenever I have head-on overlaps, right? The bond which is formed, obviously, in head-on overlap also a covalent bond is formed, and in lateral overlap also a bond is formed. But the type of bond is going to be called as now differently. It is going to be now this bond, which is formed by head-on overlap, is going to be called as a sigma bond. And whenever I'm going to have lateral overlap, and that bond formed is going to be called as your pi bonds. Right? Now if you can just connect the dots about whatever I just told, right? So here, this SS overlap, which is getting formed, and we're seeing here, right? We'll call it as a sigma bond, which is formed by an SS overlap, right? And here we'll call it as a pi bond formed by an S and P orbital. That is overlap of S and P orbital, sigma bond formed. Because like I told you, if S orbital is there, it is only sigma bond formation because it can only do head-on overlap, right? Okay. Now again, you can see that here, in this case, it is head-on overlap, these two colliding, right? So this I'll call it as sigma PP, right? And now you see that this particular is lateral overlap, two p orbitals are going. So now I'll call this as pi PP. Pi orbital is formed by the overlap of two p orbitals because it is lateral overlap, right? Okay, fine. So now that's what you understand, right? If whenever you head-on overlap, it's sigma, a lateral overlap happens, it is pi. Right. Now you can ask me, why is it that when I have only single bond in the molecule, right, the first bond formed always is sigma? What did we say? The first bond between nitrogen and nitrogen is going to be a sigma bond, and two more bonds will be formed, and those two will be pi. Not only in this molecule, any molecule you take, you always form first the sigma bond. Now, how do you understand this? Right now, how do you understand this is based on what kind of overlap is again happening, right? Now, any given day, if I have to ask you, if I ask you blindly choose which overlap is going to be more efficient overlap, blindly if I ask you, don't think anything, right? What will be your answer? Which overlap do you think will be a more efficient overlap, a head-on overlap, or a lateral overlap? Come on, it's just a blind guess. Anybody can guess. What do you guess? Okay. I wanted to go to the sorry?
Head-on.
Head-on overlaps. Okay. So I wanted to go to the chat box, right? An answer. Which do you think is going to be more efficient overlap? Head-on overlap or your lateral overlap? Head-on or lateral? Everybody will just type their answers and just put it. Whatever you think. It can be right, it can be wrong. Yeah, you put the answers head-on. Only one answer came. Only head-on overlap. Only extremely will answer. Nobody else will even take part and answer. What do you think? कितना पराठा है? आलू कम है। आलू इतना ही है। 6 होगा। छोटा-छोटा बना दो 6। Okay. Sorry. Right. Okay. So nobody's gonna answer. So you have to call the names now. Srikriti, Abhinav. Are you not gonna answer? Morally, Srinidhi. Srinidhi answered. Okay. You're not even going to give your opinion. That's how it's gonna be. See, already we know online classes how they are. Okay. Anyways, I don't want to maybe. Fine. Okay. Right. So any day given, right? Any day given, I would anyway any day choose definitely head-on overlap is going to be more efficient than a lateral overlap. Why? Because obviously it's all about how closer the two orbitals can come together. Is it not? How much close the two orbitals can come? Right. So what I was telling is the two orbitals will be able to come more closer if at all head-on overlap happens, but they will not be able to come that much closer because when lateral overlap happens, right? So any day given head-on overlap is going to be more efficient, right? Head-on overlap is going to be more efficient than a lateral overlap, right? That means what? A bond formed by the head-on overlap is going to be stronger than the bond formed by the lateral overlap. So you understand that sigma bonds are always going to be stronger than pi bonds, right? It's all about how the overlap is happening, right? Sigma bond is stronger than pi bonds, right? So now, obviously, when I say stronger, right, that means the stability or any bond which is going to get formed, right? Any bond which is going to get formed is going to give a stability. That would have been the first mantra which you have learned for this chapter. Why a bond formation happens is because I need stability. The atoms involved in the atom will gain stable, will become more stable, and that's why a bond is happening, right? So the stability which is going to be given by a sigma bond formation is going to be very high when compared to the stability given by the pi bond formation, right? So, and now if at all more stability is given, obviously the atoms will take that only first, right? So that's the reason why the first bond formed is always going to be a sigma bond. That is, after that, how many other bonds you form are going to be pi. Now you can ask me, why is it that two sigma bonds are not possible then? Then more stability will come, right? The more and more sigma bonds you form, then more and more stability will come. But we see, it's not like some random thingly you have to, understand how the overlap is happening, right? Now we have three coordinate axes, right? We have three coordinate axes, X, Y, and Z, right? So now, whenever we see that, say, S orbital and S orbital are coming, right? Now we need to have three axes, right? Okay, say like this, something, and another orbital will be like this. Say this is your, I don't know. Okay, now we have to understand. Now you see that along some axis, we have to fix that these two orbitals are coming and overlap, right? Now, please remember that conventionally, right, this internuclear axis. What is the internuclear axis? This axis, which is along which the orbitals are coming and overlapping, right? That because this will be connecting the two nuclei, right? This is not this axis connecting the two nuclei, so it's called internuclear axis, right? Now this internuclear axis was always conventionally taken to the z-axis. Means what? The sigma bond is going to get formed is always going to be along your z-axis. So this is your z-axis, right? This is your z-axis, right? And this can be y, and this can be y, and this can be x. Doesn't matter. 90 degrees apart, right? So this is your internuclear axis, and that is always going to be considered as your z-axis. Okay, right? Now what you understand is, say now another sigma bond. How is it possible? Right? If I consider your z-axis along your x-axis, along y-axis, we cannot find another bonds. That's not possible, right? Because this itself is spherically symmetric, right? So I don't know whether you're able to imagine it in 3D, right? If it is 3D symmetric, it will be already along all three axes. Okay, already along your y-axis and x-axis, you cannot form any kind of sigma bonds. But what you can do is that if at all you have p orbitals, right? If at all you have p orbitals, say this is your y-axis, right? Let me just shift the y-axis and write it like this. Okay. Now you will see that, or this is your z-axis that we'll keep, right? Now the pz, if I take, okay, now how do I put this to you? It would be like this, right? So now, right? So now again, along your z-axis, if this is your z-axis, comes your pz and pz. Now why am I saying this? Now you have px, py, and pz. All three are present, right? Okay, px, py, pz. There are three different p orbitals. That's why you put three different boxes whenever you draw p orbitals, right? Now out of these two, if I fix that the internuclear axis is your z-axis, obviously this axis is z-axis, and only along that axis the number will be there for that particular thing. I think I remember for your pz, for example, this will be the shape, and say for your py, if this is the y-axis, this will be the shape, and px will be along x-axis, right? Now if I fix that your the internuclear axis is z-axis, then definitely what you understand is the sigma bond which is going to get formed by overlap is obviously going to be an overlap between your PZ and PZ. Right? Now, please try to understand that the PZ, right, if at all it is there, it will not be able to form any kind of bond formation with PX or PY. Same goes with PX and PY also. PX can form overlapping with only PX. PY can form overlapping only with PZ. Now, how do you understand this? Right? Say if at all this is your PZ, obviously your PX or PY will be something like this, right? Because it will be perpendicular. This will be along Z axis. This will be along Y axis or X axis. Right? So how will you come and make a sigma bond? That at two, it will be a very inefficient overlap, even if you do that. That is not going to result in bond formation. Right? So if at all PZ is there, they'll be able to do this. Right? Now Z axis is done. Right? Now if you consider that this is your Y axis, right? And then say p orbitals are coming like this for lateral overlap, right? Now this is possible because now if you look at my video, right, one bond is formed like this, the sigma along your Z axis. This is your Z axis. The PYs and PYs are like this along towards you, right? Now they will come laterally overlap to make a pipe. That will always happen. Right? They'll always, now this is your sigma bond, right? The PZ and PZ came like this head-on overlap. Your PY will be like this, PY will be like this. Now they will overlap to form a pi bond. That will be very easy to understand. Right? Now that, if at all you can understand this geometry, that XYZ axis, you will understand that more than one sigma bond is not possible. On top of that, whatever you can form can be possible only by the lateral overlap of other orbitals, so only pi bond is possible. Anyways, right? Okay. So this is all about your sigma and pi bonds, how they are different, and obviously which is going to be stronger, what bond is formed first, what bond is formed after that, right? Okay. Now for you to answer the first question I asked you, right, that is this one. What is the hybridization of this molecule? Right? If you can remember, that's where it all started. Right? We went to VBT, we learned Lewis-Dawes structure, what are the different types of covalent bonds which can be formed, right? And how are they different, right? All these things we saw. Right? Now actually there is one more type of covalent bond also, right? I don't know whether you have learned about this. Do you remember or have you heard this term called as coordinate bonds? Do you know anything about this? No? Yes? So what should I understand? That you know what is a coordinate bond or you don't know what is a coordinate bond? What should I understand?
So we don't know it clearly.
Okay, that you can say that you don't know or you know this much only. Okay, fine. So when we understand, like this is also a type of covalent bond only. Okay, this is also a type of covalent bond. But what happens here is that, say, when I have a AB bond like this, right? Or now you see, understand it like this. I have AB like this. One electron comes from A. Okay, just hold on. Okay, all right. So now in a normal covalent bond, what happens is, right, you have A and B coming, two atoms are coming, and they will have unpaired electrons like this, right? And they both will be mutually shared, right? These two electrons will be mutually shared, and two electrons, the electrons are shared, and a covalent bond is formed like this, right? Now, what if I have A, it comes without it empty, it comes empty-handed. It is not going to have any electrons, but B is going to have two electrons. right? Now, what can happen is this A will be able to take up this electron and get stabilized, right? But this is a special type of covalent bond. Here what you're seeing, two electrons are there and covalent bond is formed. But how is it getting formed is that these electrons are going to be both the electrons. In this case, two electrons are shared, but both the electrons are coming from this B only and A is giving no electrons, right? But both electrons are mutually shared between A and B, right? So now how do you represent these kind of bond formations? Is you write arrow mark from where to where the electron is going. From basically you going from B and the lone pair of these two electrons are going to B and getting shared, right? So this type of bond is what is called as your coordinate bond, right? So what is the speciality of a coordinate bond? Rather than one electron coming from each of the atom, two electrons will come from one single atom and they both will get mutually shared. That is what is called as your coordinate bond, right? Now, if you want to understand this, or if you want to take some examples of where a coordinate bond can be formed, right? Let us take the example of carbon monoxide, CO, right? Now, let us try to draw the Lewis dot structure for carbon monoxide. Okay, right. So carbon monoxide, carbon is, okay, obviously, carbon is going to have 2,4, oxygen is going to have 2,6 configuration. So for carbon, I will put 4 electrons. Okay, 4 valence electrons. Right. Next, for oxygen, there are 6 valence electrons. Let us put it like this. Right. Now, for oxygen, we require 2 more electrons to satisfy its octet. Right, because it's already having 6 electrons. If we add 2 more electrons, it is going to be octet satisfied. Right. Now that's very simple. Now this oxygen will take up the 2 electrons from carbon that is mutually shared. Right. Then obviously oxygen also has to give only 2 electrons. Right. Whatever is taken, that should be given. Right. Now this carbon also takes up these 2 electrons, and now you see that double bond is formed between for this one bond, for this one bond. Now oxygen is having a lone pair and another lone pair is there, that is this, and carbon is, sorry, right, and carbon is again having a lone pair like this. Okay. Now what you understand is for oxygen, somehow you are able to satisfy octet. It had 6 electrons, 2 electrons came from carbon. So fine, now totally it is now going to have 8 valence electrons, so it's okay. But what happened to carbon? Carbon was having 4 valence electrons, right? And 2 more electrons came from oxygen. So totally that makes it 6 electrons. So 4 plus 2 is 6, right? But what is requirement for octet? Octet requirement is 8, right? So now what happens is, just because carbon is not stable, this oxygen is going to donate these 2 electrons, which is going to be there, to carbon in the form of a coordinate bond, right? Now you see that you will write 2 bonds like this with one lone pair on these 2 oxygen and carbon atom, and from oxygen to carbon, the coordinate bond is going, the electron is being donated. So there is a coordinate bond in carbon monoxide, right? This is what is called as a coordinate. Okay. Now, if you are wondering how I can connect this with the help of an overlap, that's very simple. Say, for example, I have an s orbital is coming empty, and this s orbital is having a lone pair. Now, what will happen? Same thing will only happen, right? There is just that instead of having one electron coming from here, both the electrons come from one of the s orbitals. That's how you easily understand in terms of orbitals or overlap. How do you visualize a coordinate bond, right? Now, what you can do is, I will give you maybe 2 minutes to think about or draw the Lewis dot structure for NH4 plus ion with a coordinate bond. Okay. Somehow draw the Lewis dot structure for NH4 plus with a coordinate bond. I'll give you maybe 2 minutes. And once you are done, just keep it and check. Everybody please try. Okay, I hope everybody's trying, not using your phones. One more minute. Okay, so I'll draw. You can just check whether you have got it right or not. So nitrogen now is going to have, again, so it's like obviously there is a positive charge here, right? Now, for to which out of these two atoms, that is your nitrogen atom and hydrogen atom, out of these two, which is going to have the positive charge is the first question, right? Now that is again going to be based on electronegativities. You all know what we all know what are electronegativities? Yes, no? Okay, among these two, which is more electronegative? Nitrogen, hydrogen is more electronegative.
Nitrogen.
Nitrogen is more electronegative. Okay, cool. Right? Nitrogen is more electronegative. So more electronegative atom cannot have positive charge. It will have only negative charge. Right? So out of these two, less electronegative atom is hydrogen. So that should only have the positive charge. Okay. So now what you understand is there are nitrogens, hydrogens, 3 hydrogens, and 1 H plus. That is what you understand. That is how you make a monopositive charge. Right? Nitrogen atom, hydrogen atom, hydrogen atom, hydrogen atom. And obviously how you account for 1 positive charge, along with making sure that your hydrogen is going to have the positive charge. Right? Obviously in the form of a H plus. Right? Now these are the species you have to worry about. Right? Again, we know nitrogen is going to have 2, 5 for configuration. Right? So nitrogen, I'll draw 5 electrons now. Sorry. Okay, 5 electrons now. Say 1, 2, 3, 4, 5. Right? And let us draw the 3 hydrogen atoms also. Hydrogen I know is just going to have a 1s1 or just 1 comma nothing. Right? 1 is the configuration. 1 electron it is going to have 1 electron, 1 electron, 1 electron. Okay. Now another thing remaining is your H plus. Now what is H plus? Hydrogen had 1 electron. If I say plus means 1 electron is removed. Right? So all I'll have is 1 as 0. This particular hydrogen which is here does not have any electron. H plus it is. H plus. Right? Fine. These are all the things which are going to be available in your NH4 plus. Right? Now, obviously, for each of the hydrogen atom, duplet should be satisfied. Right? It has just required 1 more electron. Right? So this hydrogen will take up this electron. This hydrogen take up this electron from this nitrogen, and this hydrogen take up the electron from nitrogen. Right? Now, obviously, you understand that nitrogen already contains. Just give me a second. Right. So you understand that what is that? Yeah. Nitrogen already has 5 valence electrons. 1, 2, 3, 4, 5. Right. Now it requires 3 more electrons to satisfy its octet. Correct. So these hydrogens already gave only 1 electron from them each. So obviously nitrogen has the right to take up to give 1 more electron also, or it is compulsory for nitrogen also to give 1 more electron and to take up the electrons of hydrogen also. So this particular nitrogen will take up the electrons which are there in the hydrogen atom, total 5 plus 3. Already 5 in the nitrogen and 1, 1, 1, 3 more are coming from hydrogens, totally 8. Nitrogen is also satisfied. Right? But what about the H plus, which we have here? Right? So for that alone, what is going to happen is, say, if this is your lone pair, which is still there, that is these 2 electrons which are here, which are not involved in bonding yet, right, will be coordinately donated to the H plus, which doesn't have any electron, and for which the duplet has to be satisfied. It requires 2 electrons, right? So now what happens? Both the electrons comes from nitrogen and it will be donated to hydrogen form of a coordinate. Right. So now, obviously, in the NH4 plus, there is not going to be any lone pair present on nitrogen. Right. So we can write that this is what is going to be the structure. But out of that, one of them is going to be a coordinate bond, and whichever is having the coordinate bond is nothing but your H plus. Other three, this, and this are normal covalent bonds. But this one, you represent it like this, from where to where this is a coordinate bond. Okay. Right. So in CU also same thing was happening, right? The lone pair on oxygen was donated to carbon, so that carbons were getting satisfied. Here hydrogen's duplet is getting saturated from H plus. Right. Okay. So I think we had good enough number of things to learn today. What is sigma bond? What is a pi bond? What is a coordinate bond? Everything, and so many things, which is stronger, which is weaker. So many things we saw. Any questions? Anybody has? Tomorrow we'll continue with respect to other topics. Okay. Yeah. Any questions? Anybody has? Okay. If that's the case, we'll wind up the class then. Thank you so much. You all can leave.
Thank you, sir.